Assalamu alaikum viewers, and welcome to my channel, and hope you are all doing well. And today's video we are going to discuss the examples related to beta function. In the previous video, in the series of the previous videos related to beta and gamma function, we have just accomplished all these things that I've just written at this right corner. You can see that we just understood what is the relationship between our beta and gamma function. We just proved all that thing, and we derived the relationship between these two functions. Then we prove in the next video after that, we prove the property of the beta function, which was this. And then we move ahead to the transformation of our beta function with respect to beta integral from the definite integral to the improper integral. And before that video, once we were on the gamma function series, we discussed the two properties of the gamma function in the part 1 of gamma integral video. So all these things are now cleared. Those who have watched those videos, I hope the concept is very much refined in their minds. So once now these things are cleared, we have now full access towards the examples. So because before approaching to the examples, once you are studying maths, it is mandatory that you should be well aware with the formulas and the relative properties and the characteristics of the subjective topic with examples you are moving ahead to do. So, and once now we have just gained acquaintance of all these relative properties and formulas and relationships, now we have got full permission to move ahead to the examples. Okay, so in this video we are going to discuss 2 or 3 examples, and in which we will learn how to handle beta integrals. Okay, so let's have a look. Okay, so this is the very first example, and we have to evaluate it with respect to beta function. You can see that over here, if we just try to compare this integrand with the integrand of the beta integral, which is this, you can see that the general form of beta integral is this. It is having integrand of this type. You can see that over here we are having power 1 on this x, okay, which is getting subtracted with this one. Instead of this, over here, once we look at this question, we are having square on this x, which is getting subtracted with 1. So we have to, it is not following the structure of the integrand which is present in the beta integral. Okay, so we have to transform this integrand exactly on the format of the integrand of beta integral. All right, so what we do, we have to apply some substitution work. We are going to substitute, or we are going to make some supposition, and we let x square equals to some variable. You can take it u, you can take t, and so on. People usually study u substitution, so they simply restrict themselves with the u. I'm taking t here, okay? Sorry. So this is it, and then once you take square root at both sides, you come to know that your x is equals to your under root t. All right, okay, now either you can differentiate this equation at both sides with respect to x in order to get your d of x, or you can differentiate this equation with respect to x. It is your choice. Okay, so I'm just differentiating this equation with respect to x at both sides. All right, that's what I'm doing. So just apply the formula of derivative of your xn. It's going to be n times x power n minus 1. So this is it. Dx upon dx equals to dt by dx. All right. So this is your 1, and you're having 2x equals to dt by dx, and you need the value of your dx only. So you just shift this dx over here, and 2x will come in the denominator. All right. just like that. And as you have to remove this x completely while you are transforming all the all the x values with respect to your t, okay, so there must not be any x over here, so you know that your x is under root t, so you just write that dx is equals to 1 upon 2 times under root t d of t. Okay, this is it. Excuse me. Now we have to change the limits as well with respect to t. Okay, so if your lower limit of x is 0, then according to this equation or this equation, your t is also going to be 0. Okay, once you substitute your x over here, either in this equation or in this equation, you get the answer 0 for the t as well. Similarly, if the upper limit of if the upper limit of your x is 1, then you just substitute 1 over here, so t is also 1. All right, this is it. So the values of the limits are unchanged here just because of the nature of the equation. So now we are going to transform this integrand with respect to t, and the form that is going to come will be exactly on the format of the beta integrand. Okay, so let's do it. Limits were same over here. Now at the place of your x, you're going to put under root t. Okay, and over here let me write it in much easier way. Let me remove the radicals and just write the corresponding powers of those radicals first, and then I'm going to substitute with respect to my t. Okay, so it was actually x power half, and 1 minus x squared was having a cube root, so 1 minus x squared is having power 1 upon 3 dx. Okay, now I'm going to make the substitution work. Okay, so now at the place of your x, you are going to substitute under root t, which is t power half actually. Let me write it down for you. It's t power half. Alright, this is it. So at the place of your x, you just write t power half and it's enclosed whole power half. Okay. At the place of your x squared, you're going to put your t power 1 by 3. At the place of your dx, you're going to put down this value because this is your dx. Okay. That's it. Alright. Now just write 1 upon 2 is a constant value outside the integral. Alright. Powers are overlapping. You're going to multiply the powers. It gives you 1 upon 4. Okay. And this t and the base are common. They are getting divided. So when the power moves up, it is going to be written with the opposite sign. So that's what we have done here. Okay. dt. Now you just simplify the powers here. You're going to take the LCM, solve out the fractions present in the power. Okay. So it gives you negative 1 by 4 and is 1 minus t power 1 by 3 dt. Okay. This is something that you are having. Now this format is exactly on the pattern of your beta integral, you can see. Now I have to obtain the value of my L and M here. Okay, so you can see that your L minus 1 is minus 1 by 4. Once you compare this integrand with your formula integrand of beta integral. you come to know that L minus 1 is minus 1 by 4, and your M minus 1 is 1 by 3. Okay, and with the help of this, you can now get the value of your L and M. You just simplify this thing, and you come to know that the value of your L is 3 by 4. Okay, and similarly your M. So the value of your M is 4 by 3. Alright, so this thing tells us that our beta Lm, which is equals to this, if therefore expressed as beta of L, which is this, and M, which is this. Okay, this is it. It's done. Now in the next step, we have almost we are coming to the end of this question. You see that when you studied the relationship between beta and your gamma function, you come to know that beta of the two real positive values Lm is equal to the gamma function product of your L and M separately upon gamma function of L plus M. So that's what you are going to follow here. Okay. So let me make some demarcation. Okay. So this thing tells that beta of your L and M is equal to, and this was actually 1 by 2 of this beta function, so I just forgot to write my 1 by 2 here. I'm sorry for that. So this is it. So 1 upon 2 gamma function of L into gamma function of your M, okay, upon gamma function of L plus M. Okay. Now as you can see that inside a gamma function you're having a rational number which is not integer at all, so it is not possible for you to express this thing in factorial form, so you're going to leave it as it is. Okay, just take out the LCM of this thing. It's 12, 9, 60. By 12. This is the answer of this question. Okay, so that's what we have done. Let's move ahead to one more example. Okay, so this is the second example that we have to evaluate with respect to beta integral. All right. Once when you try to examine this integrand, you come to know that it's not exactly on the pattern of the integrand of beta function. So you have to transform it first. So you have to do what? You have to apply letting work once again, and you assume that your xn is equal to some variable. You take it d or any other variable you want. Okay, so once when you take the nth root at both sides, once when you take the nth root at both sides, just like that. So when you remove the radical of the nth root, you are going to get the power this t power 1 by n. This and this powers, these two powers are getting overlapped. They are going to get vanished. Just x is left having power 1 and is equals to t power 1 upon n. Okay, that's it. Now differentiate both sides with respect to your x. Okay, so once when you differentiate both sides with respect to your x, you come to know that this is your 1 and over here you're going to apply the formula of your xn, derivative of xn. It's going to be n, this is the n, x, n minus 1. That's a pattern that you are following over here. And the variable is totally different from this from that of the variable involved in the differential operator, so you just write it in a chain rule form like this. This d of x will move over here okay, 1 upon n minus 1 dt. Alright, so that's it. Now you're going to replace your dx by means of this and your xn by means of this. Alright, now what is left are just the limits. So let us transform the limits as well with respect to our t. So if your x is equal to 0, then once when you substitute 0 over here, then this thing tells us that t is also 0. So t is also 0 here. And once when your x is 1, then on substituting 1 in this equation, you come to know that t is also 1. So t is also 1. So the limits are not changed here. Okay, they are same. Now let us do the transformation. Okay, so we come to know here you can see that the limits are same. Okay, at the place of your xn you're going to put down your t, okay, like this, minus half. Okay, at the place of your dx you're going to put down this value. All right, dt. Okay, 1 upon n is a constant number, so you just write it outside the integral. Okay, that's how we do. And let us organize the terms in the integrand. And minus half can be established like this. Okay, so once now when you compare this form with the integrand of your gamma integral, you will come to know that they are following the pattern. I mean, they are exactly on the same format. So here at the place of your L, you're having your 1 upon n. At the place of your m, you're having your half. So this integral is going to be expressed with respect to gamma function, beta function. This, all right. Now, according to the relationship between beta and gamma function, you are well aware with it. Sorry, it's n. That's it. So the final answer you are having you've taken the LCM of this thing, and that's the answer. Okay, so that's how we do. So I hope you have understood. I just tried to cover the aspects as much as we can. In the next video we are going to discuss few more examples of the beta integral involving sine and cosine. Okay, we are going to establish a relationship between beta between sine and cosine and the gamma function and beta functions. So that's all for today, and if you people find this video helpful, I suggest and I request to subscribe my channel, hit on the like, and share it with the other learners as much as you can, so that others will also be helped. And okay, then practice well and study deeply and be happy. Take good care of yourself. Allah Hafiz.